for me also to sit on your side and become a student, but first bench. I've always been sitting at the front, that's become a habit. So it's nice to listen to our colleagues here giving lectures on related topics and to see how things are interpreted and presented with different perspectives, different methodologies and background. A few observations I made in these lectures. Dr. Raghavendra was talking about a point in a certain space or an element of a certain space. So when you have an m by n image, one point in that m by n space represents an image. All those coefficients of pixels are defined. So one point. In the Huff domain, one point represents a circle, but in terms of the parameters that define the circle, the center, x0, y0, and radius c. So depending upon the formulation of the space, the parametric space or some space of variables, then a point in that space could represent many things. We saw in Dr. Shyamlal's lectures that the convolutional neural network can learn the coefficients and perform convolution. The coefficients could be specified by the user or could be learned by the network in response to samples provided as input and some training output. But my view has been the classical approach before ANN, CNN, and so on from the 1970s, which is when I learned these topics, signal processing, image processing, so on, pattern recognition, through my courses at IISc Bangalore. At that time, we didn't have these topics established well enough to be studied in this manner. So I could say that I prefer to specify my own convolutional matrix. I want to design my own method. I need to know what operations are being performed. And not everything is convolution. For example, the last topic I presented at the end, we needed to detect the breast boundary and find those contours and get the sort of difference between the expected contours and the angle of the oriented pattern determined using Gabor filters. Perhaps some of the Gabor filters can be given as convolution matrices, although large, and a number of them, a bank. That can also be put into CNN and DL and so on. But then there are some other things that may be harder to put into such a network. I would see that more as an implementation. And you could implement the same procedure using different formats of your program, different languages, different ways of expressing matrices and operations, vectors, signals, and images, and so on. One could say that I prefer to have my input and specify what I want as output. My children used to make fun of me that a buffet, I always criticize buffets, that I don't understand buffets, they say. I understand, but in a buffet, I can't specify what I want. Somebody else has determined what should be laid out. I've been here in Udupi for 10 days, I still haven't had my kai holige, coconut paratha, if you want to call it so. Nobody has offered me, and I keep asking, and things have changed. We were here 10 years ago. We asked for holige. No restaurant offers that. They only have, everybody has gobi Manchurian and noodles, and so they have learned the way I want to connect it to what we are talking about here is the neural network of the restaurants and hotelier business people here. They have learned what from the public, general public, all the input received, and the majority of them want ice cream and gulab jamun and gobi Manchurian and something else. I want something else, and it's hard to specify that because the network has already decided something. And the same with a thali meal. I don't like the thali meal because I don't know what is coming there. I want to specify, I want this, this, this. So the classic approach would specify and provide the user more control on what I want. Whereas some of these other approaches may not give me what I want. There was one more observation. What was that? I forget that now. Okay, maybe it'll come to my mind later on. So let's move on to this today's topic of application. By the way, I have added 5 more PDF files to the folder, and Dr. Raghavendra has already put that on your folder. Please download. There is one called CAD Intro, Introduction to Computer-Aided Diagnosis. I will not go through that because parts of those have already been covered or will be covered. The others are available. This is also available. So today we will talk about digital image processing for ophthalmology. And I've had 2 students, Faraz Alomi, who did his MSc and PhD with me, and Iris Ju, who has done her MSc with me, in collaboration with Dr. Anna Els, who is a pediatric ophthalmologist and retinal specialist at the Children's Hospital in Calgary. I mentioned 3 of my students have done MSc and PhD with me. MSc by research, by thesis. What I have always told my students who have done an MSc is go somewhere else, or at least go to a different professor in the same department. I tell them clearly, if you stay with me, you will not learn anything new. I'll simply tell you, do this and do that, and you will do it. So I would suggest the same to others to gain good experience. It is nice to have degrees from multiple universities or institutes. But I also tell them, if you do your MSc and continue to do PhD with me, very likely you will get your PhD much faster than doing a PhD with somebody else, because you have to start learning again. So a few of them took that second piece of advice. Anyway, so what is this? First, why do you want to image the retina? The retina is the detector at the back of our eye, at the back of the eyeball, onto which light is projected by the lens. And retina has sensors, rods and cones. Rods are sensitive to light. Cones have 3 varieties, maybe 4, depending on which theory you look into, that are typically sensitive to bands of light in red, green, and blue. It's not just red, green, blue, but they have a certain bandwidth of sensitivity, which I'll talk about in more detail in my seminar tomorrow on color image processing. There are several diseases and conditions of the body that can affect the retina. Hypertension, diabetes are the 2 common conditions that affect the blood vessels in the retina, blood supply to the retina, and certain things change. And if not caught early enough and treated, it could lead to serious issues leading to retinal detachment and blindness. Retinal difficulties are also caused in very premature children with low birth weight. And Dr. Anna Els was interested in retinopathy of prematurity, or what is called ROP. I'll show one application to diabetic retinopathy, but our project was mainly on retinopathy of prematurity, where premature babies below a certain birth weight and lower than a certain period of gestation will have this risk of developing retinal problems. And if it is not caught early enough and treated within a few months after birth, the child could go permanently blind eventually. So there is a serious risk there. And we were interested in that project. There are some similarities in the symptoms or the signs you see in retinal images between diabetic retinopathy and ROP. But there are some that are particular. So we started working on that project. This shows me going through the standard retinal imaging procedure. In some cases, there could be dilation. In this case, there is no dilation of the pupil. You just go and sit there, and there is a flash of light applied. You get a picture, as you see at the back on that monitor. Simple procedure, non-contact, except I have to put my chin there. In the case of pediatric infants, premature infants, they are very tiny, and they are in the intensive care unit, what is called a NICU, neonatal intensive care unit, and they are in oxygen chambers. You cannot do that. So there is a camera that is used that typically requires contact. The lens has to be in contact with the eye, and I'll show you a picture that not many may like, but I'll show that picture. So imaging of the retina is fairly simple, but not so simple in the case of premature babies. Screening for diabetic retinopathy could be done using this in adults. And there are screening programs in many parts of the world and in India too. There are many institutes and companies developing software. So this field is well established, has been established over the past, let's say, 20 years. And there are commercial systems available. For ROP, also, there are companies in Bangalore. There is Narayan Nethralaya. There is a Karnataka program for ROP called KidROP. And there are many other. There is one from Stanford University in California called SunDrop. So there are many programs for ROP also. And I believe in Karnataka there is a program where social workers or hospital staff go to rural areas and look for premature babies being born, and then scan them, or maybe they scan all children, all babies. And there are many devices being developed, attachments to cell phones, to obtain pictures of the retina of babies, children, adults. ROP, retinopathy of prematurity, is a condition that could develop in the first 8 to 12 weeks of life. It's not clear as to what causes the problem. When a baby is born so early, I'll give you some statistics, prematurely, then the retina may not be fully developed, and after birth there could be some rapid development of blood vessels. And there is some doubt as to whether the enriched oxygen supply in the ICU may be causing some of this rapid development. So let's not look into the cause, but it exists. ROP is a leading cause of preventable childhood blindness, but childhood blindness means blindness for life. The risk factors are said to be in articles: birth weight less than about 1,250 grams, less than 1.2 kilos, and gestational age less than 28 to 32 weeks. That's a range given, but in our database, those numbers are even smaller. So the next image, I gave this seminar in Brazil once, and they told me, oh, don't show such pictures without warning me first. This is not bad, but there is some imaging procedure with the camera touching the baby's eye, and some people may not like it, so if you don't like, close your eyes. So here is a little baby, and the eye has to be, the eyelids have to be opened up, and then gel is applied to the tip of this camera. This is an old video camera. Perhaps there are better methods now, but they're still being used with what's called the RetCam. And that the lens has to touch the eye in this case. We couldn't do this. We can't even get into the NICU, the ICU for children, for neonatals. So this is done by the hospital staff. And these are some sample pictures from the database given to us by Dr. Els. She's an international specialist. She has connections in India. She goes all around the world. There are big networks of ophthalmologists working on this problem, and she's a leading expert in this area. And she has developed a database from which we got these images. These are all retinal images of premature babies. No ROP. The blood vessels look normal. I'll explain what normal and abnormal are. ROP stage 1, 2, 3. The staging is not very important. Initially, scanning is to detect, initial screening is to say, is there ROP or not? And then there is a stage of ROP called plus disease, where the disease is progressing rapidly. And that is important. 1, 2, 3 may not be important. But what you see in the stage 3, where the difference is more obvious, is the angle of insertion of the temporal arcade, that is the blood vessels that go this way from the optic nerve head. That is a wide angle of insertion or insertion, let's say. This is a narrow angle of insertion. That is an artifact of the screen. And the blood vessels get tortuous. These blood vessels are piecewise linear or curvilinear structures, smooth. But here they are more kinky, if you want to use a loose term, but tortuous. And also the blood vessels are thicker than those. So there are three important developments or changes from 0 to 1 to 2 to 3. The angle of insertion of this, what's called the major temporal arcade, gets narrower. I'll show with more examples as we go along. The blood vessels get thicker. There is dilation. But dilation where is the question? All blood vessels get thinner. By the way, this is called the optic nerve head. Blood vessels come from the brain, some artery within the brain come inside here and then spread into the retina, and the veins go back that way, and along with the optic nerve, they go from here to the brain. The optic nerve carries the information, the pictorial information encoded, processed and encoded to the visual cortex in the brain. So this optic nerve head is where the blood vessels come and go, and also the optic nerve, which you cannot see. So it's a point of convergence or divergence. That's an important thing of all these vessels. So angle of insertion, thickness, all these blood vessels get thin, and then there are arterioles and capillaries, and then the venules form and the veins form, and then blood goes back. So there is a natural change in thickness. So when you say dilation, the question is, where do we measure it? That's an important question. I'll talk about that later. And then tortuosity. So these are the signs that Dr. Els described. And we set out to analyze and perform quantification of these features. So early treatment is based on the diagnosis of plus disease. It's a strange terminology, but it means ROP is going at a rapid, is worsening or developing at a fast rate. Increased vessel thickness called dilation, tortuosity, straightening of the major temporal arcade, or the angle of insertion becomes narrow. So again, compare that with this. Tortuosity and dilation, and the opening, that to this. So the objectives of our study, first you have to detect the blood vessels. To do any of this, you have to detect what is called the vascular architecture, and then analyze that. So detection of the MTA and all blood vessels, and measurement of the thickness, in particular the major temporal arcade. We said we won't measure the thickness of all vessels all over the image, it's useless. They all get thin at the end, so why bother? So they specify a range as to where you want to measure the thickness of only the MTA. MTA is the major temporal arcade. Quantification of the openness of the MTA via parabolic modeling and measurement of the temporal arcade angle. The temporal arcade angle was defined in a different study by researchers in London, England. Quantification of vascular tortuosity and CAD of ROP. That was our project. Before this, you can add detection of all blood vessels. Dr. Els has been working for a number of years, decades perhaps, on developing this database telemedicine for ROP in Calgary that is called Tropic. Calgary is not in the tropics. I don't know if she meant that as a joke, but Calgary is in the, not Arctic either, but in between. Cold, not tropic certainly, not tropical. Images were captured using what is called a wide field, 130-degree field of view, RETCAM 130, poor resolution. So this is what we got. Nowadays, I'm sure you can get better images, but the coupling is important. Yeah, you can take pictures with your cell phone, and there are some coupling cones or some kind of a device attachment, so you can focus on just the retina and not let light come from elsewhere. I don't know if the quality of the images that you can acquire with premature babies using the cell phone attachments. But it's being done in Karnataka in screening programs. The spatial resolution is not bad, but 30 micrometers per pixel. We only got 19 images. No signs of plus disease, we got 91 images. Oh, this is what I wanted to say earlier in the context of these convolutional neural networks and deep learning and the restaurant and all that I told you. Certain things are trained by a large population. Like the restaurants want to cater to the general public, not to my specific taste. They won't make this coconut holge just for me. I'm sure they know how to do it, but they won't make it because they can't sell and make money. So when you take a specialized database like this, or when you want to address, let me turn back, when you want to address a very specialized condition such as ROP, you will not get 1 million cases. You can't train a deep learning system with 19 ROP images. You can get 1 million normal images of adults. You can get maybe 10 million or 100 million around the world. But they're all normal. How many of them are ROP, of premature babies? The same with architectural distortion. You can get 1 million mammograms. In fact, from the screening program, when I asked them to digitize, scan mammograms, they brought 1,000 normal mammograms. I said, no, I don't want 1,000 normal mammograms. It'll take us a year to scan and handle them. Get me a certain proportion with abnormal conditions. As I mentioned earlier, in a screening program for breast cancer, only 0.5%, 1 in 200 women will be found to have breast cancer. Maybe 10% will have some other breast abnormalities. And of those 1 in 200, how many will have architectural distortion? Very few. So you will not get 1 million cases of architectural distortion to train. You train with 1 million normal mammograms, how can it find that one needle in the haystack that has architectural distortion? The same here. We only got 19 with ROP. And all of these are from premature babies from the Alberta Children's Hospital. We had 91 with no signs of plus disease, but various stages of ROP, and normal too. So the statistics: birth weight 800 grams, gestational age in weeks, that is when was the image taken after birth, about 26 weeks or 25 for the 2 data sets. Wait a minute, sorry. Gestational age is the period of the pregnancy in weeks, only 26 or 25 weeks. The chronological age is number of days after birth when the image was taken, about 2 months. So the gestational age or the period of pregnancy is also very low compared to the normal, which is between 36 and maybe 40. 40 is considered normal, I think. But 36 to 40 is the normal range, and these babies are very premature. And the birth weight is only 800 grams on the average. So these numbers are much lower than what the textbooks quote as the risk factor. So we also use the DRIVE database, a public database for which with which many papers have published their results of vessel detection, blood vessel detection. These images are also not of very high quality. These are from the 1990s, 500 by 584 by 565 pixels or 20 micrometers per pixel. Now this number looks good, but the overall size is small. Dr. Els marked some of these features. She traced the temporal arcade. She drew the boundary of the optic nerve head and so on. Marked the tortuous vessels for training. So here are examples from the DRIVE database. This is not pediatric. So this is the optic nerve head, the fovea that is within the macula. The dark area is the macula. And there are not many blood vessels in the macula. That's where there is a high concentration of the rods. That is where we get high visual acuity or sensitivity. So because of the higher density of the rods that are the sensors, there are not many blood vessels there. As you come to the optic nerve head, there are no sensors there. So this is the blind spot where there is no detection. The superior part of the temporal arcade and the inferior. In this case, the temporal arcade is the other way. Okay? So, if you were to look at a certain part of it close to the optic nerve head, it is approximately a parabola. As it goes out, there is some convergence back down, and the blood vessels go that way. So, for parabolic modeling, we consider only a small portion here with reference to the optic nerve head and the fovea. There are many algorithms in the literature to detect the optic nerve head and the fovea. The fovea is hard to detect. In the case of ROP with premature babies, the fovea and the macula are not seen at all. So it's not possible to detect the fovea. The pre-processing steps, we use, this is a color image. We use the luminance component from the YUV representation. I'll talk about the representation of color images later on tomorrow. But you take that Y, and that is given as this combination of RGB. That's a standard definition. So it converts the color image to just this intensity image. Or this is the intensity component of the color image, with the other two components being the chrominance components or color components. To get the effective region, there is this black area, there is this boundary which causes serious issues in edge detection on blood vessel detection, because this is a very strong edge. So to process this non-square image, that is, we are interested only in the circular part, and all the image processing algorithms, Fourier transform, they're all based on square arrays. We had to do something. So we wanted to get the effective area. What is the part of the image where you have the retinal image and the rest is background? So we thresholded by using 0.1 as the threshold on the Y channel. But then we wanted to fill this background, the rest of the black area, with some continuity in grayscale. So we applied morphological erosion with the disk structuring element of radius 10 pixels and replaced the pixels at the outer edge of the effective region by the mean over at 21 by 21 neighborhood. This is to remove any artifacts in the detection of the boundary, and then keep padding that with the average and keep going until you reach the boundary. So instead of this sharp boundary now, we have this relatively smoothened image. So we don't get artifacts related to those edges. Otherwise, those will get detected as blood vessels. So merge the effective region with the outer edge pixels to form this extended effective region, and repeat it 50 times and keep extending it by a ribbon of width 50 pixels. Apply a median filter and get a reference intensity as the maximum of in the result of the whole image. So we wanted some reference intensity as to what is the average or reference intensity or brightness of this image. Gabor filters you have seen, so I won't repeat. We are detecting oriented structures such as these blood vessels. And this you have seen before, and this you have seen. So here we have the inverted Y channel. To use the cosine function in the Gabor filter like this, it is detecting bright objects. It won't detect dark objects. If you want dark, you use the sine function to get a dark line in the middle and white side lobes. Anyway, the side lobes will be dark and white, or dark and bright. So we inverted the Y channel and got this image where the blood vessels are now brighter. The Fourier transform, it's a little hard to see. If you zoom in, you will see some oriented components. So you see that, I suppose. So this concentration of energy corresponds to blood vessels perpendicular to that. So these lines contribute to that. So by using a Gabor filter at 45 degrees, we extract these components. That is there, and this is here. Gabor filters, we used a bank of filters. This is one filter, by using a bank of 180 real Gabor filters, real meaning cosine only for modulation of the Gaussian, minus 90 to plus 90 degrees, that is minus 90 is downward and plus 90 like the y-axis. Elongation L, thickness tau, 7 pixels. These parameters were varied depending upon the application as to what you want to detect. The Gabor magnitude response at each pixel is the maximum of the filter response over all angles at every pixel for a given pixel. And the vessel orientation is given by the Gabor angle phi p, for which you get the maximum response at that pixel location. So that is the orientation field. So for this image, all the blood vessels have been detected by taking the Gabor magnitude, maximum over 180 Gabor filters. And for each of those filters, each of these pixels, you take the angle of that filter that gave the maximum response. And for this little window, you see the vessel like that, which is here. The angles agree with the orientation of the blood vessel. Those lines are drawn only for every 10th pixel because you have to draw that line. So in between also, we will get, for every pixel, we get an angle. In the background, the angle is irrelevant. So we don't have to really show those angles. We could say if the Gabor magnitude is less than some threshold, don't show the angle. But here we are showing all angles. So like this, we get the angle for every pixel in the image. And then you have to threshold this. So we tried various thresholding techniques. I won't go through all of that. Depending upon which thresholding method you use, you get some result. And in the drive database, there is a reference given, binary pixels of the vessel map that you can compare your output with. And there are many papers where that has been used. And Chowdhury, this is Subhashish Chowdhury, who did his MSc with me, then PhD at the University of San Diego. He did this work, and it's a highly cited paper. I don't know how many thousand citations for his paper, using matched filters, using Gaussian filters of different scale, matched to the orientation, rotated, and when it matches the idea there is if you take a blood vessel and if you take a section, it will have like a Gaussian distribution of the intensity in the projected image. So they used match filters, they got 0.91, but then there are many other papers after that. Once you show that, then there'll be a whole string of other papers telling, oh, you got 9.1, I'll get 9.9. So we didn't get 9.9, we got 9.5 and 9.6. And we were talking about Gabor filters, and I had met Soares in Brazil. He did a work on multi-scale Gabor filters and got 9.6. And I'm sure there are others with deep learning who can get not more than 1, but 999 something. These are area under the ROC curve with 20 test images from the drive data set. So vessel detection is well established. There are hundreds of papers perhaps on this. To detect the ONH, Iris Jew, she did her MSc on this project, and she started with the Sobel operators to get the edge map, and you get the two gradients Gx and Gy, and take the magnitude. You have seen all this threshold to get an edge map, and then apply the Huff transform. I have shown the Huff transforms for circles. X minus a plus y minus b square equal to c square, and xy equal to ab is a center, and c is the radius, and in the Huff space, a single point ABC represents a circle. The accumulator is defined as A of ABC. So the procedure is obtain a binary edge map of the image, set values for A and B, some range. We know the optic nerve head is this big. We know the dimensions, the range of the dimensions for pediatric cases and adults. So we don't want a circle that big or this small. So set a range for the Huff space parameters A and B. A and B must be inside the scope of the image, but also we could say it has to be on a certain side, but it can't be always macula centered. Sometimes some images are ONH centered. Most of them are macula centered or fovea centered. So it depends on the imaging format. So it may be difficult to set limits on A and B. So you can say we'll use the entire space of XY. Update the accumulator corresponding to, for every pixel, corresponding to ABC. Update the values for A and B in the range and go to the next step. And we put these limits, average diameter of the optic disc. It's also called optic disc. There is a minor difference between optic disc and optic nerve head, but let's ignore that. The average diameter is 1.5 millimeter for the drive data set of adult images. The radius of a circular approximation to the optic disc was put in the range of 600 to 1000 micrometers. And spatial resolution 20 micrometers, so the range for the radius was 31 to 50. So a range of, we need 20 slices. But the parameters of the 20 slices go from 600 to 1000 micrometers. This is the size of the image, 584 by 565. So here is the half space for this edge map of the entire image. We could have done something more, but at that time, Iris did this, and the circles intersect there. There's a peak there in C equal to 37, and others don't have such a peak for other values of C. These are slices of the half space. But the global maximum may not be the circle you want, so you search for a number of maxima. Select the top 30 peaks in the 3D half space that correspond to 30 potential circles indicated by the half transform. Use the property of brightness. Inside the ONH, we expect the brightness to be high normally. You will see it doesn't always work. We expect the ONH to be circular, not always. But anyway, it has to be bright typically. So we said the threshold of 90% of the reference intensity computed earlier from the entire image. So we expect this to be brighter than that. Some average value within that circle must be brighter. So this is the result. Edge map and the circle detected and the center. So this was good, but in this case, maybe. You see, there is sort of a circle here and another circle here. It's not a perfect circle. Giving excuses as to why it didn't work. But real images pose such issues. And here it is very dark, hard to see. The edge map is not showing a circle. And the best circle was that. And here there are some exudates, these yellow bright spots. So that met the condition of the intensity. And the best circle was that which is totally out. In this case, there is some region here that is so bright. That was found to be a circle somehow, but that's not correct. So we said, well, that is an interesting initial step, but not perfect. And there are other criteria we could look into. And the other one being all blood vessels converge or diverge from this area. Blood vessels, they don't intersect as such like the spicules in architectural distortion, but they emerge from within the optic nerve head and then go back there. So regardless of the intensity of the optic nerve head, this property is fundamental. Blood vessels have to come out from there and go back there. The optic nerve is also there, but you can't see that. So this convergence property is more important, and it has to be there. Not a circle, not the bright region, the previous assumptions. So we said we will use the orientation field like we did before. Now one could criticize, and one does criticize like this. Suppose I make this presentation somewhere, somebody will ask me, why did you use Gabor filters? Well, oriented structures and fine. Why did you use this orientation field and phase portrait analysis? Well, they do converge. So we have to explain as to why we chose these methods. But the common criticism is if the only tool you have is a hammer, every problem looks like a nail and you just bang on it, and whatever it is, you only have one tool, the hammer, and try to bash everything with that. That's not true in this case. We have some reasoning as to why we want to apply, and you will see that it works, this approach. So extract the orientation field using Gabor filters, filter and downsample to remove artifacts and noise, analyze the orientation field using phase portrait, post-process the phase portraits, detect sites of not architectural distortion now, but convergence of blood vessels, select a point of convergence. Now again, there are confounding factors. So phase portraits you have seen just yesterday, was it, or day before? So here is this analysis window. The image is some 500 by 500 something, and the window is 40 by 40 pixels. So within that, you take these angles, and you want to find A and B parameters. A is symmetric, so there are only 3 values. B has 2 values, so 5 values in the model to be, so that is symmetric. So what is that? So those parameters need to be estimated from these angles so that the phase portrait model will generate a flow field or orientation field comparable to this. That is through nonlinear least squares and simulated annealing, for which Fabio had developed some programs. So the project continued in that direction. You cast a vote at this point, fixed point of that phase portrait minus A inverse B. That gives you the location. The window could be there, but it says my patterns here converge there. So that is where you increment in the node map. The window could be here. It says the fixed point is somewhere there. Then you say, no, I'll throw it out. So the saddle is that where we don't have anything in this area. The node has a number of votes cast in that area. Now you post-process that, accumulate and do some filtering and thresholding. You can find the point of convergence or divergence of the blood vessels. So this is the point that was marked by the algorithm. Dr. Els drew the boundary of the optic nerve head in some of these test cases. She marked where she marked what would be called a reference point in the optic nerve head. Is that the point of convergence of the vessels, or is that sort of the geometric center? We don't know. She gave us one point, and our method gives a point. So we computed the mean distance to closest point between the contour drawn by the ophthalmologist and the circle detected. And in this case, just a point, the Euclidean distance between the reference point given by the ophthalmologist and that detected by the method, and verified the results. So for the 40 images in the drive database, the first peak in the node map, if that was used as the optic nerve head point, one point is detected, not the contour. The distance was 1.6 mean with standard deviation 2.4 in pixels. Where is the millimeter? Sorry, that is millimeter and this is pixel. In parentheses, pixels. 1.6 millimeters and 2.4 standard deviation in millimeters. If you apply the condition of intensity that around that point, if you take an average in a neighborhood, that it should be brighter than the reference, then a better point was selected, with the error being 0.46 millimeter. Now we had a question as to what was the point that was marked by the ophthalmologist. Was it the center of the optic nerve head, geometric center, as I mentioned? And we did say that this method will detect the point of convergence or divergence of all the blood vessels, but then it's not one point. You see, all of these, there is some common area there. So depending upon where the ophthalmologist marks the point, there could be some difference between what is detected by this method and what is marked as the reference. Anyway, we got a point in the optic nerve head. We just need one reference point, and that's adequate for subsequent analysis. To measure vascular thickness, we said we will use the MTA, the major temporal arcade. The retinal vascular changes can be indicative of diabetic retinopathy, ROP, and hypertension, as I mentioned. And in all these cases, there is an increase in the width or thickness of the MTA. Some call it diameter. Small changes are hard to detect by the naked eye, especially in the case of ROP. Those vessels are so small. So how do you measure or estimate the thickness and compare? It's difficult. So the processing steps were take the Gabor magnitude response, normalize and divide into the upper or superior and lower inferior parts using the center of the ONH. The center or the reference of the ONH was detected using this method that I showed. 1 point is enough. All we want is the upper part and lower part. So we can model them separately. They were enhanced using gamma correction, binarized and clean with morphological area open. The ONH and its boundary were removed, and branching points on the skeleton were removed. We got a skeleton after that. Each skeleton segment was labeled with a number. To track the MTA, a seed was selected automatically, labeled with the highest average Gabor magnitude in a region around the ONH. We have 1 point around the ONH, search, and from there the vessels are coming. They'll be the thickest. The vessels will be thick there, thickest over their path. So depending on the Gabor parameter you use, in this case we used a large value for the thickness, tau. So we detect only the large vessels, the small vessels are suppressed. So multi-scale filtering, you use the thicker scale. So find a pixel near the ONH that has a large response for the thick Gabor filter. And the next segment is the neighboring label with the highest average magnitude response, and keep going like that along the vessel. You are tracking the vessel from the ONH. So the vessel is marked into segments. I'll show some examples soon. Then we need to find the vessel edges. We have the skeleton, which is not necessarily the center line. The skeleton is somewhere inside the vessel, and then we have the vessel boundaries. To measure the thickness, we want to draw a perpendicular to the skeleton line at every angle. We have the angle, every pixel. We know the angle of the vessel at every pixel from the Gabor angle output. So we draw a perpendicular, and until the perpendicular crosses the vessel edges. So we need the vessel edges. So we compute what's called the mean absolute deviation of the Gabor angle response of the MTA segments to select linear segments. When the vessel is curving, it's a bit hard to measure. The angle is changing. So we break the vessel into linear parts. And for that, we analyze the angle. We use Canny's method here to obtain edge pixel candidates for every linear segment. Interpolate the vessel edges as two lines fitted to the edge pixel candidates on either side of a linear segment. We know the average angle of the skeleton, so use that angle and fit straight lines on both sides. And then you can measure the thickness. Obtain the normal line at each MTA skeleton pixel using the Gabor angle response. Obtain points of intersection between the normal line and the two edge lines, and MTA width is that distance between the 2 points of intersection. So this is all done automatically in the program rather. So here is an example of a case with no plus disease. This is a premature infant. The Y channel image, blood vessels detected, Gabor magnitude response. So this is only the upper part of the temporal arcade. The optic nerve head is somewhere here and the lower part is here. We analyze the two parts separately, get the skeleton, remove all these pieces, and finally we get this and break it into parts that are almost linear. This is the Canny edge output. So on either side of this line, there will be two edge lines. So for each point here, draw a perpendicular until it crosses those two edge lines. These are the perpendicular lines shown graphically. And at points where the curvature changes or the line segment orientation changes, there is a new line, a segment there, a segment here, from here to there is another, that is another segment. Or if there are blood vessels intersecting, you cannot measure thickness, so throw those points out. and for the inferior part. All done automatically, and if we don't like the word automatic, computationally. So we take the average of these, and we go only up to a certain distance from the optic nerve head reference point, which I believe is half the way to the macula. We don't have the macula, so we estimate some distance and say we only measure the thickness in this portion of the image from here to there. This distance is known through statistics. So we cut the image for that distance from the optic nerve head. Because after this, the curvature changes, the thickness changes. Where do you measure thickness? And if I measure thickness all over, then the average is meaningless. So that's the measurement. It's 111 plus minus 18 micrometers. For this case, without plus disease. And with plus disease, 125. So thicker, as you can compare that and that visually, same scale, same process. Okay, that is dilation. So we're not measuring an average thickness of an entire vessel, and we're taking multiple measurements of the actual thickness at multiple points in a limited region. So we can get not only an average thickness, but also some standard deviation if you are interested in that. So these are the points where the thickness was measured. A few tens to a few hundred points. So for no plus, 91 cases, the mean was 110 micrometers. Minimum, maximum there, let's not worry about that. Plus disease, 125. And that was significant to P equal to 0.002, highly significant difference. But the diagnostic accuracy in terms of ROC was 0.76. So sometimes the statistical p-value we found was not very meaningful. The p-value is so low, it says it is statistically highly or very highly significant, 3 stars, 4 stars, and all that. In terms of ROC, it doesn't show that. There are two very different ways of measuring the value of your parameter. But still, we quoted those, computed them. In the diagnostic situation, area under the ROC curve is perhaps more important because you want to catch not only plus disease, but also all the no plus diseases must be marked as negative. That is, you must have high sensitivity and also high specificity. And the ROC area tells you that. We tried to compare various stages of ROP, stage 0, 1, 2, and did the comparison between the various possibilities of this S0, 1, 2 to S1, S2, S3. Only comparing with S3 turned out to be statistically significant. The others were not significant. In any case, Dr. L said that staging is not important in initial screening. Our next is modeling. We said we are interested in that opening of that arcade, which we said is a parabola. Is it that big or is it this narrow? Narrowing is not good. Narrowing means there is some scar tissue that is pulling on the vessels, and the vessels are going like that. So we use the Gabor magnitude response with a large value of thickness tau equal to 16 to get the MTA, because that's what we are modeling. The rest of the blood vessels, we don't care. Binarized, skeletonized, the skeleton image cleaned using morphological area open. So this is what we get. And here again we put that limit on where we want to apply that model, only to that portion with reference to the optic nerve head. Now this is an image from the DRIVE database. Vessel map, Gabor magnitude response, skeleton. Cleaned skeleton shown with thicker lines just for display. It doesn't matter. We thought we should remove all these little pieces, but when you use the Huff transform, it doesn't matter. These will cause a little bit of noise in the Huff space, but there is a big parabola clearly there, and you could fit a little parabola there, but it is way somewhere else. We want all the parabolas to pass through the optic nerve head. Otherwise, we reject them. So some of these artifacts are not important. They can stay. If you want, you can keep cleaning further. So the equation for the parabola y minus y naught square is 4ax minus x naught. A is the openness parameter, x naught, y naught is the vertex. So again, we have a 3D half parameter space. So one point in the half space with these parameters will define a parabola in the image domain. So that we have seen. The MTA follows a parabolic path up to the macula only. And after that, it sort of bends downward or inward. Given that the macula is about 2 times ONH width, temporal to the ONH, that is in this direction, this is the temporal area of the brain. So these are also called the temples. So temporal, I suppose, refers to that. 2 times the ONH width, and that has been, statistics of the ONH width are given in the literature. And with the prior knowledge of the ONH1 reference point, we restrict the horizontal size of the half space. So the size of each plane now is the full height of the image, 580 pixels, but only 170 pixels in width for the drive images. For the tropic images, we used other parameters. So anatomical restrictions on the half space, the location of the vertex of the desired parabola in the half space is restricted to be within 0.25 times ONH width of the ONH center or ONH reference point detected previously. So we are saying, give me a parabola that is there with its vertex, not some other parabola. The value of A also has limits. That is the openness of this MTA. It can't go straight like that. It cannot be like this. So there is a certain range. So we said the range is 35 to 120 for the drive images. That is just a parameter. The number of planes in the 3D half space is 86 for this range. So here also we tried some of the concepts I mentioned earlier. If you update the half space with unity for every skeleton pixel that has remained, you get this very busy half space. One slice. This is only one slice of the 3D half space. Half space, if you take this and say, I want only the points in this region with the vertex and horizontal size restrictions, you are limiting only to this portion, and even a circle, the distance of the vertex must be less than some distance I specified with reference to the point in the ONH. We are searching only this much in the plane, half space plane, and that in 3D. If you update the half space with the Gabor magnitude, that is, the accumulator cells are not incremented with unity, but with the Gabor magnitude response of that pixel, then higher Gabor response means a thick vessel. That's what we want. And there is a vessel and not some other background detail. So all of these in this section will be reduced to just that, and you put the distance condition, it's only that much. So our search in the half space is limited to this little circle for every plane. And I said there are a certain number of those planes. So then you get to find the best fit, best parabola out of that. And for this image, we got that parabola. We have drawn the parabola with no limits on space, but the fit was done only so much, using this much of the information, as I showed earlier. Later on, we felt we shouldn't have drawn the parabola like that. Anyway, for illustration, that's the parabola that was detected. For the superior part, it is matching the MTA well, but the inferior part, the vessel is going here, it is not fitting. So sometimes there could be a little bit of rotation of the image. That is, the axis of the image, what is called the retinal raphe, joining the optic nerve head to the macula, to the fovea rather, it is like that. So the image is tilted a bit. So then we said we will split the MTA into superior and inferior parts and fit a parabola to each one and take only half the parabola. So we got that, which is having a good fit similar to that. Here we're getting a better fit. The vessel is there up to here. So we get two parameters of the two parabolas. So we call this dual parabolic fitting. So this is the contour of the MTA drawn by Dr. Els. And this is a single parabola, the red one, if you can see that. These cyan lines are the MDCP, not MDCP, DCP, distance to the closest point. So from here, find the closest point and take all those distances and average them. That gives you MDCP. And that was 11.5, but with the dual model, it's only 3.1 pixels. So there are two parabolas here. Can you see the red line? No. Perhaps you can see the red line better. That's a parabola. The green line is the reference contour drawn by the ophthalmologist, and that's the reference point in the optic nerve head with two different parabolas. The vertices of the two must be in a certain distance, within a certain distance from the reference point. They don't touch in this case. It doesn't matter. So two half parabolas better than one parabola. There is this temporal arcade angle that was defined by a group in London. We went and met them. We were hoping to collaborate, but not much happened after that. It is measured using a graphical user interface. The user has to mark some points. The user is prompted to mark the center of the ONH. A circle with a given radius is drawn on the image, and the user is asked to mark the points of intersection of the circle with the superior and inferior parts of the MTA or venules. They are veins, so venules. The TA is measured at the angle between the three manually marked points. But the method depends upon how well these are marked. These points are marked manually, and what is the size of that circle, how big that circle should be. So TA, if you take the radius to be 60 pixels, you get 156 degrees here. If you take it to be 120 degrees, then you get 120 pixels, you get 140 degrees. That is the angle. This is the ONH marked, and those are the intersection points with the MTA. 3 points have to be marked by the user. The AMTA, according to our parabolic modeling, the value was 78. If you did the half parabola or dual parabolic modeling, 72 and 78. This is no plus disease, a premature infant here. With plus disease, it is much narrower, as you can see. Both single and dual parabolic modeling gave the same answer, 10. So 10 compared to 72 is much smaller. And the angle, it was 156, 140, now it is 87, 79. So that is narrowing of the major temporal arcade. So we did some statistical analysis of significance and confidence interval and all that. 19 cases with plus disease compared with 19 randomly selected no plus cases. We had 91 cases. So the data set is not balanced. So we said we will choose the same number. We have 19 with plus disease, so we chose 19 from the other set, no plus, but we can repeat it many times. Keep sampling, what is called bootstrapping. There could be, it's up to you to decide if you want repetition or not, a replacement or not. If you want to do it many times, you have to replace, sampling with replacement. The TAA turned out to be quite good, actually. 0.74 mean area under the ROC curve. And the AMTA, also STA, superior arcade, they both gave 0.7. The inferior one did not give a good value for area under the ROC curve. So the combined model was adequate. It gave a result that is comparable with the TAA. Now it is possible to compare these and ask the question Dr. Raghavendra said, is that statistically significant? Can I claim that my method is better than that? There are methods to compute p-values between ROC curves and between FROC curves. We have done that in other studies. So there is some statistical significance that Faraz did, and the details are in his papers. So I'll not go into that. But anyway, they're all in a comparable range of around 0.7 plus minus 0.02 or something like that. We applied this to a data set of proliferative diabetic retinopathy, or PDR, that we got from the STARE data set. STARE is another data set that has cases of this PDR where you see this difference in the insertion angle. But these are extreme cases in the sense it's very close to retinal detachment, not early stage of diabetic retinopathy, but late stage. So modeling and analysis here is not really very useful in a screening situation. Anyway, we had the data set, so we wanted to check if this is useful, and it turned out to be fairly useful in diabetic retinopathy, but for proliferative diabetic retinopathy, late stages, where the distinction can be seen here, normal and PDR. And we got better AZ values. Arcade angle 0.8, the MTA single model 0.87. Here the inferior angle gave better result, 8.2. Area under the ROC curve and some other statistics. So coming back to the ROP situation, the third observation, clinically observed, and what we wanted to quantify was tortuosity. So we studied the literature and found that there wasn't much done on tortuosity, or the measures that were defined were averaged over the entire image in some way, or they were measuring some vectors and angles of some vectors, and they were not really quantifying tortuosity as such. So we said we need something very specific to tortuosity. And a vessel is not tortuous right through. It could be tortuous, then the straight segment, another part that is tortuous. So that is one thing. The other is, where is tortuosity present in the image? Which quadrant of the image, at what distance from the ONH? So you can break the image into quadrants, or you can take radial distance and say this is around the optic nerve head, and this is outside far away from the optic nerve head, and so on. So these are important considerations in clinical practice, and none of them addressed some of the questions I'll describe now that I have already mentioned, but I'll describe some more. The tortuosity of vessels increases in the presence of plus disease and also diabetic retinopathy. That's fine. It does not have a formal definition as to what is mathematically tortuous. And quantitative analysis should be clinically relevant, not just give some number. If the number doesn't make sense to the ophthalmologist, it's not useful. It may make sense to us as engineers, some fantastic number, but if it cannot be interpreted in the context of the image. I mentioned some of the gray level co-occurrence-based statistics are very difficult to interpret. I don't know what those later H11, 12, 13, 14, I don't know what they mean. There's some statistical something. And nobody has described. I went back, searched and searched, even in the original paper. There's no interpretation as to what they represent in the image. The first few, entropy, variance, fine, we all understand. So we need to derive measures that make sense to the user, the ophthalmologist in this case. The published tortuosity measures do not consider the orientation of vessels or use skeleton pixels. So they don't even consider the angle along each vessel, because most methods don't give you that information except Gabor filters. So what are the processing steps? We get the Gabor magnitude response, binarized clean with area open, skeletonized, and small spurs, small pieces of up to 5 pixel length are removed. Branching points are removed. Each skeleton image segment is labeled with a number. Now the vessels are in pieces. at branching points, you cannot measure thickness, you cannot measure anything. It's a big area there that is common to multiple, or even intersection points, branching or intersection points. Linear parts. The vessels are curvilinear, and then there could be some tortuous part, or it could be tortuous here and then straight. The linear part should be thrown away. No point in making any measurement on them. So linear parts are identified using the mean absolute deviation, what is called the MAD measure. MAD is mean absolute deviation of the Gabor angle response. So here is an illustration of that measure. So here is a vessel segment from one of the images, and the Gabor angle at every pixel along the blood vessel, not in XY, but distance along, passing along this contour. These are pixels along the contour. The Gabor angle is there's small variation, and then it changes. So there is a portion where there is not much variation in the angle, so it is straight. So no point in measuring tortuosity there. So get this normalized MAD measure, and the linear samples are these. We take out a few points that are connecting these parts. There is some variation here, not much variation here. So these pieces are linear, these two pieces. So take them away and we get these segments. This is tortuous. Is this tortuous? Not really, but we are allowing some variation. We could be stricter in defining what is linear or nearly linear and perhaps remove even that. So one of the very basic definitions that we started with was this. We said at every pixel on that contour, along the skeleton that is within the vessel, not right in the middle, it's not the center line, but in the middle, within the vessel, we said we are tracking that and we know the Gabor angle at every pixel. So all you do is compare the angle at one pixel along the vessel minus the previous angle at the previous pixel and at the next pixel along the contour, not a 3 by 3 or anything. And if the difference is small, sign is small. If it is 0, sign is 0. An average, a forward and a backward. This is backward and that's a forward difference. Two differences average the sign values. Take the magnitude, the difference could be negative, so half of that, and average that over all the pixels belonging to that vessel segment. Not the whole vessel, but that piece. And this is normalized by definition to 0 to 1. So we always check the methods or ideas with some test images. A straight line should be 0. A little curve, more and more curvature, very tortuous, that number is increasing. Tortuosity is increasing with frequency and length of that. See here, there is tortuosity, but it's reducing there. So some confirmation of the idea of what we call proof of concept. Now, how do we relate this to the clinical notions? A clinician doesn't want to get this number, AVT is some number 0 to 1. It doesn't make sense. We used an independent training set to obtain AVT threshold to detect tortuous vessels. So we asked Dr. Els to mark pieces of vessels that she considered to be tortuous. And we obtained the AVT value and then used that as a training set and set a threshold on AVT. Minimum tortuous vessel length was also determined using the training set. How long should a vessel be crossing this AVT, have AVT measure greater than the threshold in order to be substantial or significant? When I use the word significant, some others said, oh, you mean statistical significance? What is the p-value? I said, no, I didn't say statistical significance. I used significance as an English word. So when I say significant, sometimes I change and say substantial or meaningful. So what is the meaningful length before you say, yes, it is tortuous? And how long what should be the total length of all these tortuous vessels in order to say that that patient has ROP. Plus disease is diagnosed if at least 5 millimeters of tortuous vessels are present in one quadrant of the image, or 2.5 millimeter present in each of two quadrants. So that was the rule that we came up with in consultation with Dr. Els. So here is an example. This is a part of the vessel being tracked. These are the Gabor angles. Now we are drawing these lines only for vessels, not for the background. Gabor magnitude response and skeleton and trimmed skeleton. These are the linear parts thrown out. These are the curved parts. And the curved parts all pass the test of threshold AVT, so they are marked as green just for display. So no tortuosity here. These are the actual vessel segments that were detected, and analyzed, and zero tortuosity, 0 millimeters of tortuous vessels. They passed some threshold for tortuosity, but other conditions were not passed. So all of this done automatically in Faraz's program. Then this is a case with plus disease, some examples of blood vessels with their angles. Gabor magnitude response, the skeleton cleaned, linear segments removed. This is the remaining part. And here you see the don't go to the next page. The tortuous parts marked in red, just for display. Now, is this tortuous? Well, it passed all the tests. We could change the parameters, but we are measuring, there is some variation in angle. The thresholds could be changed if you wish. But that is clearly tortuous. So here are two more examples. No plus disease, just those two little pieces. So that would fail the length test. Here, many of these segments are marked. And if you were to add up in this segment, you would get more than 5 millimeters total tortuous vessel length. So that is something the ophthalmologists would understand and appreciate. There are all these blood vessels. If Yoni can show, and she could look at this image, but we could simply say in this segment, in this quadrant, the fourth quadrant, there are all these blood vessels. The total is so many millimeters. Or you can give all these numbers per quadrant. There are a few more issues that I'll mention. The AVT and the diagnostic decision-making criterion were applied to 91 images without plus disease and 19 with plus disease, and we got a sensitivity that is quite high, 0.89, specificity of 0.99, and area under the ROC curve 0.98. This was unbelievable, so I told Faraz, go and do it again and again and again, checked again and again, and it worked well. Specificity like that and will usually come with sensitivity going way down to 0.7 or something like that in most other cases. So we were really happy with this result. And this was only using that measure of tortuosity. When we combined, I don't have all of that. When we combined the other MTA thickness and opening parameter and put them through feature selection, this was selected. And if we stuff all of them together and push through pattern classification, only 3, 4, 5 parameters, we got similar results, but a little lower, like 9.7 or something. But feature selection said this is the only feature that matters, and using only this, we got this result. But this is with a small data set that you should remember. There are only 19 cases of ROP and 91 cases without ROP, but of pediatric cases, premature babies. So it is a specific data set. So as I said earlier, it's hard to build a big data set of ROP cases. Perhaps it's happening in Karnataka. If you're interested, you should contact the KidDrop program through Narayana Nethralaya. I tried to get in touch with them, but nothing happened. But I know Dr. Els is collaborating with them. So I don't know what went wrong, and we couldn't establish any connection. But anyway, we did this, and for us, after his PhD, he was my last PhD student. After that, we closed the lab and cleaned out everything, and he was very unhappy. He was almost crying, and I was happy. I'm retiring. He said, you're closing the lab and all of this. They're just computers. They're old computers, and nobody wants them. Anyway, he started his own company. He's in Switzerland. He has applied for some patents, and we have published all of these. He set up a company, and I was a consultant for his company, and Ben Lavoie, who is my co-author for the second edition of the book, was a research associate for this company. We developed more algorithms for ROP that I'm not at liberty to talk about because Faraz has the patent application pending for that. But anyway, these are the important criteria for ROP, and I was happy with this part as one of our last projects in the lab in Calgary. It seemed to work well, but as I said, we have to take this with, as you say, a pinch of salt and say, well, the data set is small. We applied for more grants, and as I said, granting agencies and reviewers think in a different way. Sometimes we would criticize and say, they're on a different planet, they're on Mars or somewhere. They would say, okay, get 1 million cases of this and 1 million of that, and get 10 ophthalmologists and get them to draw contours 10 times. It's impossible. You can't do that. And they want the statistics. How many babies are born premature? We had that. And how many of them have ROP in Canada? Maybe per year, 10, 20. They said, oh, we don't care. How can you say you don't care? It's an important problem. We didn't get grants, so the project sort of stopped there. So many of these projects do not progress beyond a certain stage because of various other factors. Academically and in terms of research questions, they are interesting and worth examining further. If a baby goes blind for the rest of his or her life, then that's a disastrous thing. But if you say there are only 10 such babies born in Canada, Canada has a population of 40 million, half of Karnataka, I think. So they say, well, doesn't matter. But around the world, if you say, the research is not only for Canada, it's for the whole world. Sometimes research grants are competitive, so you have to find something to push you out, some limitation. Anyway. So the conclusion is what we all believe in, that image processing techniques are wonderful and they can solve all problems in the world. Engineers can solve all problems. So image processing can assist in quantitative analysis. Again, I keep emphasizing quantitative, and pattern recognition techniques can facilitate CAD. And CAD of ROP can assist in improved diagnosis, analysis of the effects of treatment, and clinical management. So not only diagnosis, in my last lecture on Friday, I'll talk about some general things, no equations, no pictures, just general chatting as to what is all this about, where do we want to go with this. But not only diagnosis, but analysis of effects of treatment, we try to do that. Dr. Els does the treatment also, there is some laser therapy and cryotherapy and so on, they do that. And then we want to check after the treatment, has the MTA angle changed or something has happened, and we got an even smaller data set. Not enough for statistical analysis. We got a few cases before and after treatment and compared, and yes, we could see change as expected, but not enough to clearly say with statistical confidence that the method works. For that, we need a bigger data set. So we got a few grants from various agencies, and Paola Casti in Rome, she did part of her master's and PhD with me in Calgary also. And Eliana Almeida from Brazil, she had come to my lab to do part of her work on lung disease classification, and April Ingram, she prepared the tropic database. So that is about this project. Any questions about this?
Sir?
Just a minute, yeah.
So here we used dual parabolic modeling. So I got to learn that this is not very sensitive to check in the early stages.
What do you mean by that?
We are getting this for retinopathy of premature baby, isn't it? So this method, dual parabolic modeling, will not be sensitive in the early stages.
How do you say that? What makes you say that?
I just read it somewhere right now.
You read it somewhere?
Yeah.
Okay.
I was just reading the limitations of this work, and I added that it is not able to capture individual variations, and it can overfit the data set.
Overfitting the data set depends upon the number of samples in the training set and as compared to the test set. So overfitting in pattern classification is a different issue. If the data set is small and you're making a small number of measurements, or you're making a large number of measurements, then you're overfitting to that data set. And if your test set is too small, then that matters. About whether it is sensitive to early stages of ROP, that we have not tested because we only had we had an uneven data set. We didn't go from one stage to another to compare. We did that with thickness. One of them I showed, right? What was that? Oh, perhaps you're right. Let me go back to that. No, that we did with MTA width. Is this what you're referring to?
Yeah.
That was with MTA width, not the parabolic model, where if you compare no ROP with stage 1 ROP, these are the p-values. This is not significant. And comparing S2 with S0, second stage, with no ROP or first stage, that's not significant. Comparing S3 with any of these is significant. That's for MTA width, the thickness measure, not for the parabolic model.
So
Is that what you meant?
Yeah.
Yeah, okay.
Yesterday we saw that with factor reduction, we found breast cancer symptoms 15 months prior.
Yeah.
So was there any case done with this also? Because preventive is better than finding.
No, we cannot. How can I do that here? Because the babies are premature, the imaging is done, and we get the image. There is no, you cannot go backward for the babies. We don't have images. Well, the images are taken, I don't know how many times they take the images. What we did, which I don't have here, is we compared the images before and after treatment. Once it is diagnosed, there is the treatment applied by Dr. Els and her colleagues, and there is some expected change. But that happens over time. It doesn't happen immediately. And some of those images were obtained just for a handful of cases. I don't remember if I could check with Faraz's thesis and tell you what exactly was done and how many cases we got. But we didn't have enough cases. So in this case, it is not possible to do something like breast cancer screening where a woman who is, let's say, 50 years old has gone through the screening program for, let's say, 10 years from the time she was 40, and she would have 5 screening sessions. In this case, there is no such thing. But after treatment, we had a few images. So before and after treatment, we compared. And we saw some changes that would agree with the expectation, but we didn't have enough data to do statistical analysis. So I cannot conclude, as we did for the architectural distortion prior mammogram case. It's not possible here. Is that what you asked? Yeah, okay. That possibility is not here.